Okay, so this next example, we got this kind of before and after picture. 4 comes in, coming out from here, 45 degrees there, and at speed of 4 coming in, that's for ball A, and then ball B is coming in at an angle of 60 degrees at a speed of 3. And then if we think about the after picture, really the best way to do this is kind of think of the 2 directions, the parallel to the line of tangent of the common tangent between the 2 balls, and then perpendicular. So afterwards, oops, that's not very good, is it? Anyway, afterwards, we're going to have a component going out this way and a component coming out this way. We can call them, I think they're going to call them X, aren't they? So we'll call it XA and XB going out that way. The vertical component there, the one that's parallel to the line of tangent, the common tangent of the 2 spheres, is going to be the same as it coming in. So as it's coming in, this is going to be 4 sine 45 this way. So you're going to have 4 sine 45 out that way. And then it's going to be 3 sine 60. Okay. So we know those components parallel to the common tangent are going to be exactly the same. Is this XA and XB the speed of these that are going to be the bits we're going to have to concentrate on? So first bit, let's look at the restitution. So for restitution, you've got them coming in at 4 cos 45 there and 3 cos 60 there, but they're coming together, so it's an add. So you're going to do 4 cos 45 plus 3 cos 60 is the combined speed of approach. And we times that by coefficient of restitution, which is 3/4. And that should give us the speed of separation, which is, because they go in opposite directions, again, we're going to add these, XA plus XB. Okay? Then, let's look at conservation of momentum. This is all perpendicular to the tangent, this tangent here. So we look at the conservation of momentum coming in. We've got 4 cos 45 times the mass of that one, which is, mass of A is 1. The cos 60 though is going in the opposite direction. So for our conservation momentum, we're going to have 2 times 3 cos 60 there. Is that right? Yeah. And then the momentum afterwards is going to be, this has is 2, isn't it? And that's 1. So it's going to be what we said, the positive direction. That's the positive direction, we're calling that. So that's going to be 2xb, and that's going in the opposite direction, so that's going to be minus xa, 1 times xa, because that has a mass of 1. Okay, so I'm just calling this the positive direction for my conservation momentum. And then it's just a case of working through and getting what xa and what xb is. Okay. So that's 1 over root 2 times 4, so that's 3 over root 2 plus 3 times a half, 3 over 2 times that, 9 over 8 equals xa plus xb. And then on this equation, plus 44, so it's going to be 4 over root 2. And this is going to be, that's a half, so it's 3. Equals 2xb minus xa. Add them together. We're going to get 3xb equals 7 over root 2, and what's that? 24 over 8 minus 24 over 8 plus 9 minus 15 over 8. Divide through by 3, and you get 7 over 3 root 2 minus 5 over 8 for your xb. And then we're just going to stick that into, what should we do? How about this one here to get what xa is? So we're going to get 3 over root 2 plus 9 over 8 equals xa plus 7 over 3 root 2. What am I doing? Oh yeah, minus 5 over 8. Ooh, so that's what, 14 over 8? And 7 over 3 is a 9. 16 over 3 root 2? I think is what xa is. Whew. Right, once we've got those, excuse me a minute, let me just see, I'm going to check the answers first. Let's see. It's got for xa 7 root 2 over 6 times by root 2 top and bottom. Yep, that's right. Minus 5/8, that's right. And then for xa, root 2 over 3 so times by root 2, 6, 8. Is that right? That's 7 over 4, yeah. I made a mistake there. 7 thirds. So how many thirds do I have down there? 9. I'm subtracting. Dearie me. So 3 says a 9. So that's 2. Oops. That's better. Times by root 2, so 2 root 2 over 6. So root 2 over 3. Yeah, that's right. Cool. Okay, so we've got our xa and our xb. Now just to work out the kinetic energy, we're just going to do, we're going to have to kind of combine these two to give our overall velocities. So we're going to have to do Pythagoras on that. I'll tell you what, I'll shorten this and just briefly describe what we're going to have to do there. Let me just get rid of that now. So we know kinetic energy before, that's a funny F. Anyway, kinetic energy before is going to be, that was 2, isn't it? So it's going to be a half times 1 times 4 squared plus a half times 2, isn't it? Times 2 squared. It's kinetic energy before. Equals kinetic energy afterwards. Now, for afterwards, we're going to have to, like I said, do a bit of Pythagoras on this to get our overall velocity for here. So it's going to be half times 1 times, now then, here we've got 4 sine 45, and which we're going to have to square and add to xa, which is this horrible thing here, 2 over 3 root 2 plus 14 over 8 squared. Don't have to worry about square rooting it to get the actual velocity, because obviously then we're doing v squared there, so we can leave that. Plus, do the same for this one, do Pythagoras, getting your kinetic energy. Sorry, there's your kinetic energy before, there's your kinetic energy after, so if we subtract those two, that will be our kinetic energy lost. So we still got to work out the kinetic energy there. That's how to do it anyway. Whew. There's the first part.